Bond length. When atoms combine, they do so at a particular distance, and this distance is called bond length. One might think adding up the radius of these atoms would easily give you the bond length, but it doesn't work that way. The actual bond lengths are determined by X-ray diffraction and spectroscopic methods. But since I do not have the technology to illustrate, I'll be using the computer-aided program GaussView 5.0 to determine the actual bond length and the bond energy of atoms bonded together and what that means for their bond strength. Notice the radius of each atom is not the same. They are different and they increase down the group and decrease across the period, and the affinity or craving for electrons, which is electronegativity, differ and decrease down the group and increase across the period on the periodic table. To determine the actual bond length, the distance at which bonds separate is plotted against the energy required to separate these bonds. We will use hydrogen gas and hydrochloric acid as examples. In the case of hydrogen gas, which is two atoms of the element hydrogen, the two atoms are first combined, and because they have the same cravings for electrons, no one hugs the electrons more than the other. The distance between the atoms is taken and the energy recorded. We are scanning the bond distance by 0.05 angstrom decrease and increase to get the potential energy surface diagram. Next, it plots the graph. Notice when the distance was pulled too far apart, the energy levels increased, and when they were pushed too close, the energy levels also increased. The lowest level of potential energy of our graph is the global minimum for hydrogen gas, which is 0.75 angstrom. The experimental value of hydrogen gas is 0.741 angstrom. Our result is close to the experimental number, showing its accuracy. Next is hydrochloric acid. Hydrogen is bonded to chlorine, which has a greater atomic size and is more electronegative, meaning chlorine would hug more shared electrons. To determine the actual bond length, the same procedure is carried out on the bonds. The lowest potential energy level is 1.28 angstrom. Notice that the bond length is higher than that of hydrogen gas, which is due to the atomic radius and electronegativity of chlorine. Now, what does that mean for the bond energy? Notice, although hydrogen gas has a shorter bond length than hydrogen chloride, its dissociation energy is higher than that of hydrogen gas. In chemistry, the smaller the bond length, the stronger the bond strength. Therefore, hydrogen gas has a stronger bond strength